So an exponential function is a function whose equations contain a variable in the exponent. That's going to be the big thing for you here today. The variable is in the exponent itself. Many real-life situations, including population growth, growth of pandemics, we just lived through one, radioactive decay, and other changes that involve rapid increase or decrease can be described using exponential functions. So here's what the basic type of exponential function looks like. There's no quote-unquote parent function because the base would change for each type of parent function. But an exponential function with base b is written like this. F of x equal b raised to the x power, or y equals b to the x power, where b is called the base, because it's the number with a power, the base, and b is always going to be a positive constant other than 1. So it has to be bigger than 1 and it has to be positive. And x is any other number that you can plug in from the real number line. So first things first, let's make sure we know how to evaluate an exponential function. The exponential function f of x equal to 42.2 times 1.56 raised to the x models the average amount spent, f of x, in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 4 hours? So since they wanted us to evaluate 4 hours from the start of this study, that means that I'm simply trying to find f of 4. So really all I'm doing is plugging 4 into the exponential function itself. 1.56 raised to the 4th power. These are not going to be really questions that we necessarily do in our head because unless the number you're multiplying by is a nice pretty whole number, you're not going to be able to do it in your head. So in your calculators right now, we're going to type that whole thing in there. So 42.2 open parentheses, 1.56 close parentheses, then raise that to the 4th power. What do you get? Yeah. And since this question itself says to round to the nearest dollar, how should we actually answer this? 249.93. Full dollar, no cents. 250, yeah. Rounding to the nearest dollar wants no decimals, no cents. I would have rounded it to 0.93 because dollars and cents, but whatever. Do what it asks. So again, evaluating, especially for exponentials, are probably going to be calculator questions for you unless it happens to be a nice pretty number like 2 or 3 or something like that. Let's graph some exponential functions so we can remember what they look like. Again, you've probably seen these before. This is already completely done, so we're just going to highlight some important things. If we were graphing 2 to the x power, all we would need to do is gather some coordinate points to be able to graph. If we plug in -3, it's 2 to the -3 power. Bonus reminder that when you're dealing with exponents, a negative exponent means that you take that term to the denominator, and now it's positive. So this is 1 over 2 to the 3rd, which is 1/8. So we've graphed -3, 1/8. And by we, I mean the computer, and it did it very accurately. We do the same thing for a bunch of coordinate points, and then we play connect the dots, and we see that this is what the graph would look like of 2 to the x. Here are some important things for us to notice about this function. Number 1, it has a domain of all real numbers, which totally makes sense because we learned in chapter 2, I think, that there are only 3 types of functions that do not have a domain of all real numbers. One of them is the square root, one of them is the fraction one, wow, I'm blanking on the word, rational function, and one is a logarithmic function. This is not that. However, its range is restricted. Do you see how its range is only from 0 to infinity? That means that there is a horizontal asymptote for this graph that the graph is going to get very, very close to but never touch. And for us, it's the x-axis right now, y equal to 0. So everything in my graph is going to be above that horizontal asymptote. Okay, those are going to be the important things that we look for when we're graphing these, that you have the correct y-intercept or plugging in of 0, and that it's growing or decaying, and that it does not cross the horizontal asymptote when it should not. Can we try graphing one together? Let's go look on the back. Let's just see what our prior knowledge does for us. If we're graphing 1/2 raised to the x power. Do y'all remember if that is going to grow or decay? It's going to decay. The factor with which we're multiplying by is a 1/2, which means we're going to get smaller each time. But let's just do some values of this function. Let's do -2, -1, 0, 1, and 2. Those are going to be the numbers we plug in. It's just like surrounding the y-axis right there. So if I do g of -2, that means I'm doing 1/2 to the -2 power. But I have a fraction. So there is a rule with fractions and exponents that if you're raising a fraction to an exponent, you can raise the top and you can raise the bottom separately to those powers. I'm doing a lot of this to start reviewing your exponent rules, by the way. I know you have a calculator in your hand and can just do this in one fell swoop, but we can practice. Then we have negative exponents, which means they flip to the other side of the fraction. So this is 2 squared over 1 squared. Well, 2 squared is 4 and 1 squared is 1, which means when I'm at -2, I'm going to have an output value of 4. There's my first coordinate. 1/2 raised to the -1 power. Again, I can distribute that -1 to both the top and bottom, and since they're both negative, I can flip them over, but that would end up just being 2 over 1 or 2. If I plug in 0, what's anything to the 0 power? No. It's 1. Anything to the 0 power is 1, which is kind of wild. And then we have 1/2 raised to the first power, which anything raised to the first power is just that anything. So now I'm at 1, 1/2, and you're going to do your best to do a half. And then if I plug in 2, this is going to be 1 squared over 2 squared, which is 1/4. So again, do your best on that one to try to get it to be approximately 1/4. And if we play connect the dots here, do you see how my data is getting smaller and smaller rather quickly? It would look something like this. Now it's not actually getting flat down there, even though the way I just graphed it, it kind of looks like it's flat. The reason it's skimming off to the side is because, again, we have this horizontal asymptote of y equal to 0 that we have to make sure we do not cross and we do not touch. So me being human, I'm going to get as close to it as possible, but it's not going to look great. A computer would do a much better job graphing that. So let's review some characteristics of the exponential function. We've already kind of talked about this, but this puts it all in one place. The domain of the function is all real numbers. No restrictions on the domain. However, there is a restriction on the range. It's only going to be above 0 or above the horizontal asymptote. The graphs of all exponential functions of the form f of x equal to b to the x pass through the point 0, 1 because f of 0 equals b to the 0 and anything to the 0 power is 1. Therefore, the y-intercept is 1 and there is no x-intercept for a typical exponential function. Remember, we can't touch the x-axis. If the b value, the number in the parentheses, is bigger than 1, that's when we have an increasing or a growth function. If the number in the parentheses with the power on it is between 0 and 1, that's when we have a decreasing or a decay function. The fifth thing we know is that b to the x, is 1 to 1, which means it is a function and its inverse is a function. It passes the HLT and the VLT. And then number 6, we know that we have that horizontal asymptote along the graph, which for the most part is always going to be here at y equal to 0. So we have growth equations, we have decay equations, we have horizontal asymptotes to deal with, we have domains and ranges to talk about. Now, of course, these are all basic versions of the exponential function, where we can start to transform the exponential function and move it around the graph with the same rules that you learned in chapter 2 about transformations of functions. So just thinking back to when we were in chapter 2, if I started this off with f of x equal to 3x, that's what's graphed on my picture, and I want to graph g of x equal to 3 to the x plus 1. I've changed this by putting plus 1 inside the function, inside the exponent. So what kind of transformation did I just apply to this by putting plus 1 inside the function? Is it a horizontal transformation or a vertical transformation? If I see plus 1 inside tells me that transformation is going to be horizontal. Inside is horizontal. And since I'm adding 1, does that mean I'm dilating this, stretching and shrinking it, or am I moving it left and right? Oh no, we forgot everything. Fall break did us in. This is a horizontal translation, which means I'm going to be shifting the graph left and right. And since I see plus 1 inside, that means I'm moving this graph to the left 1 unit. So all I have to do is take all of the input values and move them to the left 1 unit. What's nice about this is I have all of these coordinate points already listed for me, these 3, that I can just move around. So I'm going to move it to the left, and I'm going to move this one to the left, and I'm going to move this one to the left. And as we move it to the left and then we play connect the dots, we can still see that my horizontal asymptote has not changed. It still has that boundary line down here at the bottom of y equal to 0. Can we try another one, see if we remember our transformations after a little bit of a refresher on vocabulary? So this time, again, we have a graph that was already given to you, and in that graph, we see f of x equal to 2x is graphed. It's my growth function with a base of 2. But I want to create the function g of x equal to 2x minus 3. That minus 3 is on the outside, so what kind of transformation is this? It's a vertical for sure. Vertical what? Vertical shift or vertical translation? Am I going up or down? How many units? Down 3. Because I see that minus 3 is on the outside of the basic function itself, so it's going to be a vertical transformation. But what's nice, because I already have all of these coordinate points, I can take every single one of them and move them down 3. So here I go. I'm going to go. I know okay, let me zoom in because I was just going to go through this fast. They're not perfectly coordinates right here, but you can do your best. So this is 1, 2, 3. 1, 2, 3. Then we get nice coordinates, even though it's covered. And then 1, 2, 3. 1, 2, 3. When we play connect the dots this time, it might be tempting to do something a little crazy, but we have to remember that now that we've shifted this graph down, what else have I shifted down? The horizontal asymptote. It was originally here. This is where the first horizontal asymptote is, but since I'm moving things down, I also have to move that horizontal asymptote down to where it is now y equal to negative 3. Since everything shifted down, that horizontal asymptote shifts down with it. So a conclusion we can draw is that our horizontal transformations will not affect your horizontal asymptote, but your vertical ones might. Now, of course, you spent all of Algebra 2 and a lot of pre-cal dealing with graphs of functions and transforming them. That's cool and everything. We get a lot of interesting applications when it comes to exponential functions, especially when we introduce base E. Base E is an irrational number symbolized by the letter E that is not a variable. That is like pi or I. It represents something mathematically. The irrational number E is approximately equal to 2.718 or 2.72. It's called the natural base or the natural number. If you're Googling stuff online and they call it Euler's number, which is spelled like this, that's the same thing, Euler's number. It has a bunch of different names. We normally call it the natural base E or just base E, but it is Euler's number. The function f of x equal to e to the x is called the natural exponential function. And a lot of things actually grow in nature with this base. And it happens so often that we stopped using it as a regular number and started to give it this number e for the natural base. Okay. In example 6, it says, the insatiable killer, that's the reputation the gray wolf acquired in the United States in the 19th and early 20th centuries. Although the label is undeserved, an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, the population was reduced to 800 wolves. The figure below shows the rebounding population in 2 recovery areas after the gray wolf was declared an endangered species and received federal protection. The exponential function f of x equal to 1,144 times e to the 0.0325x, that's a mouthful, models the gray wolf population of the western Great Lakes, f of x years after 1978. Okay, we got a lot of information going on here, but some really cool application. Let's save some wolves. Part A says, according to the model, and just so you remember, the model is talking about this equation right here. That's the model of the function. What was the gray wolf population rounded to the nearest whole number of the western Great Lakes in 2018? Okay, first things first. If I want to figure out the number of gray wolves that are in 2018, what number am I going to plug in? It's not 2018. Our X is representing the years after 1978. So how many years after 1978 is 2018? 40 years. So what this tells me is that X is equal to 40 because it's 40 years after 1978 is when it's 2018. So that's what I'm wanting to do. I'm wanting to plug in 40 to this function. So we would do f of x, f of 40 equal to 1,144 times e to the 0.0325 times 40. And here's where it gets fun. Let's see if we know how to type that in our calculator. Because we have this natural base e, we have to find that button on our calculator. So follow along with me. We type 1144, open parentheses. Just kidding, not open parentheses. What am I doing? We need E. Where on your calculator do you see the little e? Right above ln. It's also in another spot. Do you see it somewhere else? You get choices. Right above division. You get to choose which one you use. It's actually nice to use the one above the ln, the natural log, because it already gives it an exponent, and we're writing an exponent as well. If you ever don't need the exponent, you would use the one above the divide symbol. 0.0325, open parentheses, 40, close parentheses, and then enter. When I do that, my calculator spits out to me 4197.675 round to 4, but it wants us to round to the nearest whole number because we're going for the nearest wolf. You can't have half a wolf. So what is the approximate population of gray wolves in the western Great Lakes? 4,198 wolves. Look at them making a resurgence. Good job, guys. Now, part B is interesting. It says, does the model underestimate or overestimate the gray wolf population in the western Great Lakes in 2018, and by how much? here's the deal is they actually gave us this information in the table. Take your highlighter right now and I want you to highlight this last bar of the second bar graph. That's what's describing the Western Great Lakes. And in 2018, it says that there are, like they counted them, there are 4,222 wolves. So since the chart shows 4,222 and our formula gave us 4198, did we overestimate or underestimate the number of wolves by our model? We got we didn't get enough, right? That means that our model underestimated the population. And by how much? All we have to do is 4222 minus 4198, and we would get 24 wolves. So we were off, but that's pretty good, especially for something that can't control for wildfires or other natural disasters in the area that might affect the population. So that's pretty good. Good job, model. When we come back from lunch, we're going to look at one more applied example of when you would use exponential functions and especially the base E. And it's all about money. Money, 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 money. But we'll go to lunch first. I'm hungry. That's all I can think about right now. Another application of exponential functions, or again, especially the natural base E, is compound interest, which has to do with investing your money. So this is important things for our futures. So the formulas for compound interest, there are two of them. The one that is most commonly used is this top one, which I'm going to highlight in blue. For n compounding periods per year, meaning that it's compounded or your money is recalculated and redistributed monthly, daily, quarterly, semi-annually, those sorts of words you would see. This is the formula you use. This is the amount in the account. P is the principal investment, or how much you're putting in at the very beginning. That's a 1. Plus the rate in decimal form divided by the number of times it's compounded, raised to the number of times it's compounded times T. So this is a formula you would use to find compound interest when it's compounded monthly or semi-annually, that sort of thing. Our second formula is for what's called continuous compounding. This one is A, the amount in the account, equal to the principal investment, how much you put into the beginning, times E, the natural base E, raised to the rate times time. Rate is in a decimal, time is in years. So we can compare different investments depending on the type of investment quality you get and how it will grow in the bank or grow in the market. So let's look at example 7 here. It says you decide to invest $8,000 for 6 years and you have a choice between two accounts. The first pays 1.20% per year compounded monthly. The second pays 1.19% per year compounded continuously. Which is the better investment? Okay, so we're going to calculate both investment styles for both formulas with this information and see which one gives you the most money at the end. So for our compounded monthly, we're going to use the blue formula, A equal to P times 1 plus R over N to the N times T power, which means we need to fill in a P for principal investment, an R for the rate, an N for the number of times compounded, and a T for time. If we have all of that, it will tell us the amount in our account after all of this information. So if we reread the blurb, what is our principal investment? $8,000. What is the rate at which we are compounding for this one? This is the 1.20%, which if we make that into a decimal, it's 0.012 as a decimal. Move the decimal point twice with the Dr. Pepper rule. The N is the number of times it's compounded per year. So if I say monthly, how many months in a year? 12. So the N here is 12, because that's monthly. And the time is how long this is happening. So how long are we investing this money? 6 years. If we have all of that information, we just have to plug it into the formula to see the amount in this account. So it would be 8,000 times 1 plus 0.012 divided by 12 raised to the 12 times 6 power. But there is no variables left here, so we're not solving anything, we're just evaluating. So in your calculator, when you get a moment, go ahead and type in all of that in one fell swoop. So you're going to want to use parentheses, you're going to use your fancy fraction, you're going to want to use, again, parentheses, all of that good stuff. When you type all of that in, you should get 8596.9335, which if we answer the question, meaning it's money, let's make it look like actual money, this investment account would have $8,596.93. So in 6 years, you earned almost $600 by telling the bank, hold this. And they held on to it for you and they paid you for it. So that feels pretty good. Passive income, everybody. But let's see if the other investment account is wiser for us to use. It says this one pays 1.19% per year compounded continuously. And the compounded continuously formula is A equal to P times e to the RT power. So for this one, we need 3 things. We need the principal investment, which you guys have already told me is 8,000. We need the rate, which is 1.19%, or as a decimal, that's 0.0119. And then the years has not changed. We're still investing this money for 6 years, and so we want to see if this is a better investment. I recommend, this is kind of how I've always done like physics and or applied problems for myself, is listing out all the variables I would need so I make sure I have all of the pieces of information. If we go ahead and throw that into a calculator, this would be 8,000 times e to the 0.0119 times 6 power. And again, you would need that E button on your calculator to calculate this. When you do that one, you should get 8,592.08595, which if we make that look like money with dollars and cents, that's 8,592.09. So they're really pretty close, but like which one is technically the better investment in these 6 years? The first one. So since that's the question here, which is the better investment, we conclude that the better investment is the 1.20% compounded monthly. Again, it's nice to have a bank hold on to your money if you get these good type of investments, because they're just giving you money for letting them hold your money. Questions, comments, concerns? Yes.
What's the Dr. Pepper rule?
Thank you for asking. It's Dr. Pepper rule. I just was talking and didn't even question the fact that I don't know if I talked about that. So the Dr. Pepper rule is how to change from a decimal to a percent. Dr. Pepper, DP. If you have a decimal and you want a percent, you move the decimal point twice this direction to create it into a percent. And if you have the percent and you want a decimal, you go from P towards D, you move the decimal 2 places that direction. So for us, that one was 1.19%. So I moved the decimal 2 places, boom, boom, Dr. Pepper rule, and made it 0.0119 as a decimal. Dr. Pepper rule.
Thank you.
You're so welcome. Any other questions? Fabulous. Okay, that is 4.1.